Can the girl see that document?
No,
Not
not
yet.
You're not here.
Still sharing.
Okay, now we are
Yes, now it has come.
We are seeing it.
teacher.
We're now seeing it.
No.
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 Auntie, I removed
So
it.
now it's gone.
Now it's gone. Now do you see it?
Yay!
Yes.
Yes,
Okay.
teacher.
Joel and Angel Kasacha, please pray for us. Joy Angel Kasacha.
Father God, I want to thank you for today. I want to thank you for all that you've done for us. And God, as we go through this physics lesson, God, come and be with us and help us understand whatever our teacher is going to teach. In Jesus' name, I do pray. Amen.
Amen. We have decided to move on. So somebody can read us the subtopic.
Machine.
Machines. When did we first encounter those things? Machines.
P7.
P7.
P6.
Yeah. That's when you first encountered machines, or that's when you first studied them?
First studied.
studied.
Okay, so when did you first encounter machines?
When I was a baby.
At home.
When I was a baby.
When you were
Baby.
a baby, you understood.
When I was
machines.
born.
Okay, when you were born.
Okay.
Okay. So we have been using machines knowingly and unknowingly. I hope we agree with that.
Yes.
Some of these machines have been our personal innovations. Others we have just been carbon copying and using, copy paste and use. Is that okay?
Yes, teacher.
Okay. What is a machine? S4. Don't read the notes. What is a machine? P7. I want primary knowledge of machine.
A machine is a
May I
device
try?
by means of which a
We don't have order, girl, but did we prove? Okay. Let us have order. So they are going to select you.
There is Letitia, there is Daphne, Atkwase.
Okay, maybe we select someone else. Okay, Letitia.
What is a machine?
Letitia, unmute.
Chami, I think a machine is any device that helps us simplify work.
Okay, we can also get.
Any other deviation from that definition? We have to save time. This guy, if you are not responding,
Amelia, Nadunga.
Yes. A device is, a machine is a device made by man to ease work, to ease his work.
Okay, so all of us agree. A machine is a device that simplifies work. I think that definition is still acceptable. Okay? That definition is still acceptable. However, we modify it because we discover that when you are using this machine, you have to use certain forces, and the forces applied at one point, and they are supposed to overcome a certain load at a different point. Is that okay?
Yes, teacher.
So always, whenever we are using a machine, we'd use a certain force, and when we use that force, what is the force that we use? The force applied on the machine.
Effort.
What? The effort.
Effort.
So we have the effort. And then what do we overcome using a machine?
The load.
The load. This is we have to overcome a load. Is that okay? So in our notes, we have a machine is a device by means of which a force is applied at one point, overcome a force at some other point in order to ease our work or in order to simplify work. Okay. So the force applied to the machine is called an effort, and the resistance to be overcome is called the load.
Load.
I hope that is clear.
Yes, sure.
Now, machines do the following activities. We engage machines to do any of the following. Some machines combine those activities. There are three. Can you ask somebody to read those activities, which machines perform? Esther, let me listen from Esther, or we get something like that. Esther.
Yes, a machine is used to Roman 1, convert energy from one form to another. Roman 2, amplify a force. Roman 3, magnify movement.
Okay. Now, Roman 1. Anybody who can explain Roman 1? Converting energy from one form to another. What does that mean? We have been dealing with energy conversions. We have not read them all. By the way, let me tell you, read your notes about energy conversions. We have decided not to talk about them because we believe you can do research. So research about those notes we have left behind about energy conversions. But you can tell us what are the energy conversions? The machine. We have
Naroga, Genevieve.
Naroga.
I think like the solar, like when they convert the sun to like light. Yeah.
So you are simply converting light energy to what?
I'm not sure.
You are not sure. But you have just discussed one machine. Do you know that, you people? You tell me what that machine was.
An engine.
An engine. Very good. An engine. An engine, a petrol engine and a diesel engine was the most recently discussed machine. It converts what energy?
Chemical energy to heat
Chemical
energy
to
heat energy to kinetic energy.
To
heat energy to kinetic.
To kinetic energy, or what if it was mechanical energy. Very good. So an engine is an example of a machine. And actually many machines are of that nature. They are not broken down. There are systems. There are a combination of things. A machine is basically like that petrol engine. It is a combination of very many things, but is basically used to convert that energy from one form to another. Now, let us discuss Roman 2, amplifying a force. What does that mean? What is to amplify? Let us be
increase.
Guyana High School is known for English. Now, for you people, you are busy rotating in your natural languages. Amplifying.
We have Ayoki.
Ayoki, what is to amplify?
No, I left my hand up, sorry.
There's Paula Kazina.
Instead of us giving an answer, she's wasting energy.
To amplify is to increase or
Very good. It is to make bigger. Is that okay? Yeah? Is that okay? Yes.
No.
Yes.
Get a dictionary. Do you have a dictionary close to you? The one who says no. You don't have a dictionary. Who has a dictionary? A dictionary nearby, you can use your phone. Look up the word amplify and you tell us exactly what we mean. I would have run over these notes, but I always remember that they are not newspapers. I try to make sure that we understand what we are talking about. That's why I'm asking you the definitions of those words. So what is to amplify?
We have Eunice Nakuya.
Eunice.
To increase the volume of sound, especially using an amplifier.
This girl has gone to volume. Is that okay? But by the way, when we talk about volume, it is also misplaced.
Talk about
volume, the sound, yeah? But then there is the volume, the space. But to amplify is to make bigger. Is that okay? In the simple word, we have something and we amplify it. Let me give you a simple story. A certain boy gave Jesus 5 loaves of bread and what? How many fish?
2.
2
fish. Used to them to feed how many people?
5,000
people.
500.
What did it? And there was remainder. You can imagine how much remained.
12 baskets.
12 baskets. Very good Bible readers. So what did Jesus do?
He amplified.
He made bigger. And this is what we
multiplied.
God expand in me, God multiply in me, God amplify me. You can add that language to your prayer. So Jesus amplified, made bigger. So to make bigger, machines have that ability also to make bigger. You put in something small, it is magnified or made bigger. Is that okay?
Yes.
Remember, that is all easing work. All that is done in the cause of easing to make a task easier. Then Romans 3. Read Romans 3. What is the next purpose of the machine?
Magnifying.
To magnify. That word magnifying can actually be used the same as amplifying. Is that okay? At this time, we are magnifying movement C. Now, listen, some of these funny things are like this. Let us look at something that is very simple. I want to give you a very simple example. How do you start a car?
By turning on the engine.
What do you do to turn off the engine?
The key.
Use a key. A key works like a switch. Some cars have keys, other cars have a button. I think there are people who are seeing cars with buttons. To start the engine, you simply press a button, isn't it?
Yes, teacher.
Now, that is basically what we call magnifying a Kickstarter. You start something, you simply use a very small effort altogether, but it starts something very big. Most generators, you only go to a whatever. For example, let me give you the other easier thing. A bicycle. You keep rotating your legs, isn't it?
Yes, teacher.
Very small movements resulting into very large movements, you riding bigger distances. So you are magnifying distances. Is that okay?
Yes.
Have we got an idea of how machines work?
Yes, teacher.
They will do any 3 of those, or at least all of them. Some machines actually have the capacity to do all of them. Like a car, it does all of them, the car engine. Is that okay?
Yes.
Okay, so we are not going to look at complex machines. For us, we shall break down each of those small activities that machines do by defining our machines as simple machines. Am I making myself clear?
Yes.
We make them
Yes,
very simple machines. So when we are discussing machines, I don't want us to start thinking in terms of a car engine, a generator, a hydro station, whatever, those kind, because they are all machines. But please, we are going to deal with what we refer to as simple machines. Machines that do very simple activities. Is that okay?
Yes, teacher.
Okay, before we break down our machines, by the way, before I break down these machines, let us break them down. What are some of the machines that we have? I'm not going to follow that. Can you tell me the system of machines that we follow in our physics? So the machines, our categories of machines, how are they classified? How are they? Number one,
Levers.
we have the levers.
Pulleys.
We have the pulleys.
We have the pulleys. We have the screws.
Which are the wedges?
Inclined planes.
Teacher, and wheels.
Wheels. Number six.
Yes.
Wheels and axle. Wheel and axle.
The wheel.
Yes. And the hydraulic press.
Axle. Okay. Number 8, we shall discuss hydraulic press. But this one is not going to come right now because it will come under pressure. Is that okay?
Yes.
So we are going to concentrate. These ones are also a little bit of our syllabus. So the machines we shall be discussing will be levers, pulleys, screws, inclined plates, gears, wheel, and axle. Is that okay?
Yes.
Okay. Now, before discussing, yes, order in this class. Somebody has a lot of activities in our background.
Accuser.
Okay. So we are going to first discuss what are the terms that we use. There is a language we are going to be applying when we are dealing with these machines. So we have to understand, we are going to be talking about specifically forces. We have two forces. So we have the first is what we refer to as
work done. Work input.
Okay, we start with work input. I think we start with an input. What is it?
Effort.
Work done by effort.
What is the effort? What is that? That is the force. Which force is that?
This is work done by the effort, and it's the product of the effort and distance moved by the effort.
What is that?
What is an effort?
Me.
The energy. Machine to overcome the resistance.
I'm going to check.
Effort is the force applied to overcome the load.
So this is the force applied. Force applied to overcome the load. Okay, so you have introduced another word. What is the load?
Amelia, I don't know whether just forgot your hand. Amelia, what is a load?
What is a load?
Load is the resisting force.
The resisting force to be overcome. by the machine.
By a machine.
That will be overcome by our machine. Is that okay?
Yes.
Existing force, and that force must be overcome by the machine. Now, please take note. These are forces. Most of us forget that load and effort are forces. Altogether, the force applied, the force to be overcome. It is very crucial because some of us misunderstand them and take them to be different things. But when we talk about the load and the effort, we are talking about forces. Okay, then when we talk about the load and the effort, we talk about the load distance. Number 2, we talk about the distance, the load distance. Okay.
The distance moved by the load.
Not under, but when we talk about a load distance, what is it? What distance are we referring to?
It's the distance moved by the load.
So it is the distance moved by the load. What about the effort distance?
The distance moved by the effort.
Refer to distance moved by
the effort.
Moved by the effort. Very good. Now, all these machines are going to be describing those distances. There will be a distance described by the effort. There will be a distance described by the load as we use the machine. So we must understand, refer to them as either distance moved by the load or simply load distance, or distance moved by the effort, or we refer to it as the distance and the load, the effort distance. Is that okay? Are we good to go?
Teacher.
Yes. Do we have a problem?
No.
Yes, teacher. Yes, teacher.
We can't see the board clearly.
I have erased everything on that board. Okay. So what I hope you can see the board. Oh. Now, girls, we are going to start dealing with very important terms. Those ones were the beginning ones. Now you have that term in your thoughts. We refer to it as the work input. What is the work input?
This is the work done by the effort.
Who is that one speaking? We don't want ghosts. We want people. Put up your arm and you speak to us. That was Kajimu, I think, or somebody. I had somebody's voice. Kajimu Namuga Jovia. Give us the answer properly.
The work input is the work done by the effort, and it is the product of the effort and the distance moved by the effort.
Is that okay, girls? So our work input is the work done by the effort, and it is the product of the effort and distance moved by the effort. And we have that equation. So I'm not going to be writing that on the board because it is already in your notes. That is our work input. Is that clear?
Yes. Yes. Yes,
teacher. And the Naruga, do you have questions?
Oh, teacher, no, I wanted to read, but it's okay.
You are going to read the next question. I mean the next term, work output. Can you read it down?
Work output. This is the work done by the machine to overcome the load. It is a product of the load and the distance moved by the load. Therefore, work output will be equal to load times distance moved by load. Therefore, its work output is equal to L times DL.
Okay. Now, under work output, I want you to put in brackets some other term. You put this as the useful work. You always come up across that. That is what we also refer to as the useful work. Useful work, that is what the machine is intended to do. Am I making sense?
Yes. Yes, teacher.
When I say that is the work that the machine is intended to do, what do I mean? Who can explain that statement better? Who can it? Put up your arm and tell us that is the work the machine is intended to do. So Angel Tongo, tell us what we mean, expound.
So I think you mean when you say that, you mean like for a car, you can sit in a car and it takes you somewhere, and then it's going to produce sound, it's going to produce heat, but it's not intended to make that sound, no, to bring that heat, but it's just intended to transport you from one place to another, maybe.
Okay. So when you are moving from one place to another, you are going to discover that your intention is for you to move, isn't it? Plus your luggage or plus your load, those are the things that you really want to move. But in the process of moving, you come along with the car, because without it, you cannot move. So you are carrying the useless parts of the machine. Am I making sense?
Yes, teacher.
Yes, teacher.
This is what I really mean. I'm going to draw what she has given us. I have a pickup. I am transporting matoke.
Excuse me, sir, I haven't really understood that. Can you please explain?
You are understanding. Look at what we are doing. So this is the passenger. This is the luggage. Out there. This is your machine. The car is your machine. Is that okay?
Yes, teacher.
What are you taking?
The matoke.
Your matoke. Is that okay?
Yes.
So your purpose is to move matoke. The matoke is your load. How to get?
Yes.
In this load, you go to the car, because the car has to come along, whether you like it or not. Is that okay?
Yes.
Yes, teacher.
Yes.
You have some other person. Okay, let us move it like that. So what is the total load you are moving?
Teacher, we can't.
You're muted.
Okay. So your purpose is to carry the load, not the weight of the car. Because you are not going to sell that car, you intend to sell matoke, isn't it?
Yes.
Yeah.
Yes, teacher.
Yes,
the total
teacher.
weight you are moving is what weight?
The load.
And that composition makes your worker input. Is that okay?
Yeah.
Yes.
This is your worker output. Am I making sense?
Yes, teacher.
So the load is our
Yes,
output,
teacher.
but the work input involves carrying both the load and the weight of the car. I hope you get the point.
Yes, teacher.
So the purpose of this car is to carry the load. That's why I told you that work input, that is what the machine is intended to do. It was designed to do that activity, to give you that work output. Is that okay?
Yes.
So in the process
Yes.
of work, it has to carry some useless weights. I hope you get my point.
Yes, teacher.
Yes,
Now,
teacher.
this work output plus the sum of the work done against this useless weight makes our
Work input.
Very good. That is the principle of energy conservation. Okay. Okay, so I have explained the difference between.
Please, when you re-explain the point,
Please note, I want you to note that always work input must be greater than or equal to work input output. Your work input, I'm writing here. the work output, no, the work input must always be greater than or equal to the work output. There is no way where you calculate and find that input is less than the output. That is already a wrong calculation. For most machines, our work input must be always bigger than or equal to the work output. Is that clear?
Yes, teacher.
Yes, teacher.
Yes,
teacher. Kazina, please, you have a question.
Yes, sir. I'm currently interested. So I'm sorry to take you back. I haven't really understood like the point you're trying to explain with this car illustration. So I'm still confused.
I've not heard what Kazina is saying. She says she's confused.
So I'm saying I haven't really understood the point you're trying to explain with this car illustration. Please may you explain it again.
This is what I'm trying to explain. What have I written, underlined? Read the statement I've underlined on the board.
Work input is greater or equal to work output.
Is that okay?
Yes, sir.
Now, what is the formula for the work input?
It's work is equal to effort times distance moved by the effort.
Is that okay?
Yes.
Now, what is this equation for work output?
Work output is load times distance moved by the load.
I hope that is clear to you. Now, what I'm trying to say is very simple. When you are using a machine,
Part of the board.
okay.
So
When
long
you are
as
using, don't over complain. I have heard and I'm adjusting. Listen very carefully. Are you listening?
Yes, teacher.
When you are using any machine, this is what you want the machine to do, to overcome a load. Is that okay?
Yes, teacher.
The load, I've given you the example of a car. Our car is our machine, isn't it?
Yes.
You want to transfer matoke to the market, so you load it on the car or the machine.
Yes.
Is that okay? So what is your total weight? The total weight will be the load and the weight of the car, isn't it?
Yes. Yes.
Now the engine of the car drives that matoke and the load to the market.
The matoke and the car itself.
The matoke and the car itself. Is that okay?
Yes.
Yes.
So the engine is carrying the load and the weight of the car. So it is doing the work which you refer to as work against work on the load, and it is also doing work on the weight of the car. Are we together, people?
Yes, teacher.
So that total work which is done by the machine, because it is the machine that is putting in the effort, is what we refer to as the work input. Am I making sense?
Yes, teacher.
Now, hold and listen very carefully. Your intention is not to go to the car with the car to the market. Your intention is to take matoke to the market, to take the load, not the car. That is the major purpose. You could find other means of carrying this matoke. You could walk them, you could do whatever, but as long as you're transporting them, you have to go with this car. It becomes an unnecessary evil, if I may put it that way. So if you have to go with this car, you are going to carry both the load and the car. But your intention is to carry the load, isn't it?
Yes, teacher.
So we are saying that this is the purpose of the car. This car, what it is doing that is useful is to carry. So for you, you are also going to carry it, but it is because it is inevitable, it is simplifying work for you. So this work which it does against its weight is almost negligible, or it can be of some use. That's why you put in fuel and so on and so forth, isn't it?
Yes, teacher.
Yes.
So we are saying that this total work that the engine does must overcome both the load and the weight of the car. So that's why we say that the work input, the work done by the effort, must always be greater than the work done on the load or the work output. There is no way where the work output is greater than the work input. Am I making sense now?
Yes.
Yes, sir.
Okay. Okay, so I hope I'm making sense. I want to make that point at that particular point there, that you must always know that work input is likely to be greater than the work output for most machines. The reasons is because of these useless weights. Is that clear, girls?
Yes, teacher.
Yes, teacher.
Yes,
We
teacher.
are going to see other reasons why the input is always greater than the output. There are so many other reasons. Maybe some of you are already aware of these reasons. Can you give me some of these other reasons why this work output is always less? What does the machine always overcome? Let us put in any other thing that will reduce the efficiency or the work. Number one, I've had friction. Can you explain how friction reduces that? Explain yourself, please.
Using that car.
Use the car and explain the friction.
Teacher, pardon on your question.
Let us first allow the person who has said friction. We are yourself.
Teacher, I'm not so sure.
There's a toddler, a baby who doesn't mind what she's doing. That baby doesn't mind whether you are studying physics or she's concentrating on his issues.
Shona.
However, she's disturbing us.
Is it Shona? Shona is the one who said friction?
Yes, teacher.
Okay. What is friction? What is friction for? Of what is friction?
It's the ability of a machine to hold on.
No, leave alone the machine. What do you understand by friction? What is friction? Maybe that's why you can't explain. What is friction? Okay, there is Kasasha. Let Kasasha help you. Angel.
Friction is a force that opposes motion when two objects move against each other.
Okay, now can you bring it in here? First of all, do you agree that the work input has to overcome friction as well? Angel? Angel?
I think so.
Can you try to bring it in? Your definition should help you explain why.
When a car tires wears out while after moving long distances.
Yeah.
There's another hand up.
Yes, teacher.
Your S2s. Those who have parents who have cars, in case you come back to school when you have not learned how to drive, you would have a big problem because that's one of the activities you should learn. Do you know that?
Okay.
I can ride a bicycle.
Can we come back to the
Let us come back to the class. That is an activity, I'm telling you, an assignment. Try to make those parents realize that you are grown.
Okay. Johanna.
Yes, friction reduces efficiency because when two surfaces slide past each other, friction resists their motion. And
so in the car, what happens in the car?
Use this case study we have on the chalk.
Maybe the tires of the road.
Pardon?
Some extra work will need to be done.
Continue, you are almost there. To do what?
To overcome friction and again go past it and accomplish the
task. Yeah, thank you, Johanna. That's it.
That's very good, by the way. But let us put, let me, this what I want us to know, and that's why I'm giving you the task, that if you have a parent, and this parent is a serious, if parents are listening to me, by the way, these girls are old enough to drive. 18, they'll get their licenses, but learning to drive, it is okay. Let them learn to drive, not from other people, but from you. Now, back to the point. These two tires have wheels that rotate. Is that okay?
Yes.
And in most cases, there is something that they call, you take a car for servicing. And in most cases, what is done to service a car is to basically lubricate the moving parts of a car. There are so many moving parts of a car, but basically here we are interested in the wheels, the tires, and so on, isn't it?
Yes.
Yes.
So if those tires are not well lubricated, you are going to cause wear and tear. Wear and tear will cause resistance to motion and so on. So you are going to discover that as the car moves down, the wheels are rotating. They have to be well lubricated in order to reduce the friction that will stop that rotation of the wheels. Is that okay?
Yes.
Yes.
So in languages of machines, the machine must be well serviced. And part of the servicing is to lubricate or to reduce friction in the movable parts of the machine. Is that okay?
Yes, teacher.
Okay, let us move away from there and try to at least finish these terms. Next term is, there's a chat, somebody in the chat is talking.
I think they are sending to you direct. I can come and check.
Work input must be bigger than A, okay. Okay, thank you. Okay, mechanical advantage. Anybody who can tell us what mechanical advantage is? Read for us. Sanyu. Okay, Sanyu. Zora, you will read the next one, velocity ratio, but let's Sanyu read for us mechanical advantage.
Mechanical advantage, MA. This is the ratio of load to effort. It's written as mechanical advantage is equal to load out of effort.
Okay.
MA is equal to L out of E. It has no unit because it is a ratio of forces, in brackets, quantity with the same units.
Thank you very much. So our forces, both load and Newton, are measured in what unit? Since they are forces, what is the unit of the load?
Newton.
And what is the unit of the effort?
Newton.
So since the units are identical, then that ratio, a mechanical advantage, has no unit. It is simply a value. Is that okay?
Oh, yes.
Now, the mechanical advantage will always give you how much effort you have to apply to overcome a specific load. Am I making sense?
Yes. Teacher,
Yes, teacher.
Let us understand what mechanical advantage fully is. We just talk about that, but we don't tell. But these are the labels of certain machines. A machine will give you that its mechanical advantage is equal to 2. Are we together?
Yeah.
Okay. Now it is you are given a load of 300, 200 newtons. So they ask you, what is your effort? 20,000 newtons. What will be your effort?
40,000.
It will be
10,000.
Be sure.
Be sure. If your effort is bigger
40,000.
than, what is it?
40,000.
Work out
10,000.
With you.
10,000. 10,000.
Is that okay? It is 10,000. Yeah, because the effort will always be equal to the load divided by the mechanical advantage. Is that okay?
Yes.
So this will be your load divided by 2, which will be 10,000. If your machine has a mechanical advantage that is less than 1, you are in serious trouble. Are we together? If your machine has a mechanical advantage that is less than 1, you are in serious trouble. It is no longer a machine. Okay, it is a machine, but this will most probably, the only machine that has this thing working for it is called the, what have I written?
Screw.
A screw.
Screw.
Now, anybody who can tell me what is the very special with the screw? I want you to apply these things and understand them better. Why should a screw have? That's the only machine may be allowed to have that
Excuse
accent.
me, Mr. Sir.
Yes.
I got logged off because of my connection, and I'm just confused as to what we're doing right now.
You'll read through the notes there on MA.
Okay, we are talking about the second term, which is mechanical advantage, and we are saying it is a load over the effort. And I'm telling you that for most machines, the mechanical advantage should never go below 1. And I want somebody, except for this machine here, the screw, and can somebody tell me the reason? Let us first reason why it should never go below 1 for most machines. And it is in the definition of a machine. You tell me what a machine is. First, tell me what a machine
that simplifies work.
It is a device used to do what? What is a machine?
Machine is a device by means of which a force is applied at one point to overcome a force at some other point to ease work.
Okay, give the simple definition.
That one will not get what you are talking about. I want you to give
A machine is a
device
that simplifies work.
That simplifies work. Is that okay? Now the work you are supposed to be simplifying, you must be using as little effort as possible to overcome as large a load as possible. Am I making sense?
Yes, teacher.
Yes.
Most of us, by the way, don't want to work. Do you know that? Let us start with ourselves. We don't want to work. So we want, if we want to do work, we want very light things that will not take a lot of energy.
Easy.
Easy. Even when I'm setting numbers, you ask me, teacher, what topic? That is it. Altogether, it wants to use as little effort as possible in order to get a load. We want 100%. You understand?
Yes.
Yes.
But we want to use as little effort to get this 100%. So that is how a machine is. It also wants to use as little effort as possible to get the maximum. I hope you get the point. That is the reason why mechanical advantage should never be less than 1, because it is a magnifier. Am I making sense?
What about it?
Supposing you had a load of 20,000, for us to get a mechanical advantage of 1, the effort also has to be 20,000. Because when you divide 20,000 divided by 20, you get 1. Now it means that for you to overcome a load of 20,000, you have to apply again a load of 20,000. So what work are you simplifying? So that is why he says, even when it is 1, you're already not a machine. So you need something, like you have said, that magnifies. You put in little, small effort as possible to acquire, to overcome a larger load. That is why if the mechanical advantage is 2, we realize that the effort was 10,000. In this case, it means that you need half the load. Yes. If the load is 20, I need an effort of half of it, 10 to overcome it. So if I even can use 5,000 to overcome a load of 20, it means that the mechanical advantage
would be what? What would be the mechanical advantage? Let us calculate it.
20,000 divided by 5.
Divide by 5. What do we get? Is that okay? So the larger the value of your mechanical advantage, the smaller the effort you apply. And that's why they use the word mechanical advantage. You understand an advantage? If I have of high mechanical energy, I mean mechanical advantage, it implies I'll apply as small an effort as possible to overcome a big load.
Noela Kasemire. Noela.
I'm confused because you first told us that we have to apply more effort to like move the load.
No.
No one told you
You are the
that.
only one who had that.
When we're talking about the work input and the work output, you said that the work input has to be more than the
work input must always be greater than the work output. I did not talk about the effort then. That one will come in a different way. You'll see it coming.
Effort is a force. Work input, remember work done is force times distance.
Force and distance.
So there's some implication of distance there when you're talking of work input. Are you getting the difference?
Yeah.
Yes. Once you say work input, there's an implication of force. But here we are simply talking about the load, forces, a load and an effort.
So girls, are we okay?
Why does a screw have less mechanical advantage?
Why does a screw have less mechanical advantage? Do you have a screw? Can you imagine a screw? You don't have it. But can you imagine? Can you tell me how a screw is made? I think it has very rough edges.
Yes.
Do you remember that?
Yes. Yes.
It is very rough. Is that okay? And its roughness, what does it increase?
Friction. It increases the effort needed.
There is friction. Is that okay? So the friction in the screw is very, very big, and it is very, very necessary because a screw is expected to hold certain machines or certain parts together so that they don't come apart. So that is the reason why a screw has a lot of friction to prevent motion between those two surfaces that it is holding. And for that reason, it has a very friction is necessary for it. That's how it does its work, to prevent motion. Is that okay?
Yes, teacher.
When you screw two parts together, they must remain together. So there must be no movement between those two parts. In order to achieve that, you have to have a lot of friction that will oppose that motion. And therefore, that's why screws have a lot of friction and therefore very low mechanical advantage. Is that clear now?
Shona's hand is up. Keep down. Daphne, your hand had been up sometime. Namgab. I don't know whether you just gave up.
So my hand is not up.
No, it was. I thought maybe you gave up because we were not calling you, but it's okay.
So have we understood why screws have a mechanical advantage less than one?
Yes.
It is because of what?
They have to overcome because of the friction. Because
of the friction, high friction. Is that okay? And that friction is necessary for them to do their work, because for them, they are supposed to prevent motion. That's their intention. So that's the only machine which we are going to view that has a mechanical advantage less than one. For all your calculations, if your mechanical advantage is less than one and you're not dealing with a screw, then you know you are in trouble. I hope that is okay.
Yes, teacher.
Okay, lastly, let us borrow. Mr. Bato, please, I hope you are in the background. Our last term is the velocity ratio. I hope that is it. Okay, velocity ratio. Read for us. Velocity ratio. Please read it.
Anna Grace.
Anna Grace.
velocity ratio. This is the ratio of the distance moved by the effort to the distance moved by the load in the same time interval. And velocity ratio is equal to velocity of the effort out of velocity of the load. No unit.
That's no units. So lastly, velocity ratio is what?
Distance
There's another definition.
Divide by distance moved by the load.
Now, listen, girls. This is a velocity ratio. Its true definition is velocity of the effort to the velocity of the load, but we don't but don't use it because we don't need the history, how it comes about to be reduced to this, what we use. Is that okay? Are you listening to me?
Yes, teacher, we are.
Yes, teacher.
Because it is very, very important that ignore this. I'll have students who ask me velocity ratio over effort. I'm not going to answer that question, and I'm not even going to bother. Whoever has a question on that, please forgive me. Go and do the research. What is velocity ratio? What do we use?
Distance moved by effort.
Distance by effort divided by distance moved by load.
That is all we need about the velocity ratio. Lastly, efficiency. Who is my everyday girl? She has disappeared. She has been discouraged. Shona.
Okay. Amelia.
Amelia, efficiency.
This is the ratio of work output to the work input expressed as a percentage.
So
work
that's
out.
how we.
And
go
which
ahead.
symbol?
There is a problem here. I don't know whether these ones can be edited. This should be input.
Teacher, is it input up or down?
No, it is input down.
Work efficiency is equal to work output out
This
of work
one,
input.
I'm trying to edit something here, please.
Make sure you
It is
edit
like
in your
that.
notes as well.
The ratio of mechanical advantage to velocity ratio also gives efficiency. Let's use
It is not used as a definition. We don't use it as a definition. When we are defining efficiency, please use ratio of work output to work input expressed as a percentage, or you can replace this word power with power. Okay? Now, the rest of those things, I'm going to ignore them for the proof. Ignore them. This is all that I need. Is that okay?
Yes, teacher.
This is all that I need. So this one is just for those who are interested to study more, but please, the first two is all that I need. Are we together?
Yes, teacher.
Yes, teacher.
So we are ending here. We're not stretching Mr. Bato. He has been very patient with us. And I hope we shall be able to move from, keep in touch with those terms, please. Make sure you know what we're doing. Everyone, we want to wish you a great day.
Yeah, thank you, teacher.
Thank you, teacher.
Thank you, teacher.
Thank you, teacher.
Thank you for hosting.
Somebody is saying, can we say mechanical advantage? Yes, in layman's language, but you cannot describe it like that. But it's an idea. The higher the mechanical advantage, the better the machine.
Okay, teacher.
Yes.
Nice.
So it is something that you go and look out for. Those are the terms that people use. What's the mechanical advantage? Then you know how good the machine will help be useful to you. Thank you.
Thank you too.
As we want to leave, we allow Mr. Bato